Hello, everyone. Welcome to our rocketry presentation today. I'm just going to screen share real quick.
Yeah.
Okay, so this is our NASA student launch team, LALC. And our presentation is about our rockets and the competition of NASA student launch and TARC. So about our team.
这个那个双胞胎他们就
Our team is a group of high school students from California. There's 7 students in our team. Our team name is NASA Student Launch LLC, and we are joining the NASA Student Launch organization competition with the Young Engineers in Action organization. And this is our launch of our subscale rocket. This is it's pretty small, but yeah, that's our rocket. And we got invited to the NASA Student Launch Program from getting 10th place in the TARC program. And that's how we got invited. This is a NASA Student Launch is a rigorous challenge that every month there's a new deadline that we have to meet and report we have to write.
Yeah, I get it.
So this is our team structure. We have 7 members. Our captain is Catherine Liu. She's a 12th grader at Oxford Academy. Our chief operating officer is Emily Wren. She's 10th grade at Diamond Bar High School. And this is Lee Marquez. He's the chief safety officer, a 9th grader at California Academy of Mathematics and Science. I'm Neil Marquez. I'm a TARC officer, and I'm 9th grader at CAMS as well. This is Rohan Nair. He's a STEM engagement officer, and he's 11th grader at Cypress High School. This is Andrew Liu, outreach officer, and he's 9th grade at Oxford Academy. And this lastly is Jessica Lee. She's our finance officer, and she's a 10th grader at Oxford Academy. And our team is all from different backgrounds and different schools. So working together is it's very diverse and it's a good experience. This is our social media outreach. We have social media accounts, so you can get outreach for our rocket team and about rocketry in general. And if you want to go to any of these websites or follow us at any of these social medias, you can do so. Now, these are the rocket components that we're going to be using for our rocket. So these are the basic rocket components. We have first the nose cone, then the upper body tube, the lower body tube, the fins, and the motor containment, motor holder. And we have a rocket right here. So for this rocket, this is the nose cone. This is the lower body, upper body, and this is the lower body. And fins are attached to the lower body. They're glued on with epoxy. And our motor holder is right here. It's attached to the bottom tube. So what our rocket holds is on the front upper tube, we have 1 egg and 1 altimeter. So the egg is the challenge, and we have to make sure it comes down safely without breaking with the use of parachutes. And our altimeter tracks the height of our rocket. And for our recovery system and propulsion, we have a parachute in the bottom tube, and we have a parachute in the bottom tube and a rocket motor, which is attached to the motor holder on the bottom. So body tubes are cardboard tubes. We use cardboard tubes for our TARC rocket, and for our NASA rocket, we use fiberglass tubes. And these tubes, they hold all the components inside, and we paint it to be smooth so that there's less drag, and so that the rocket will launch. The nose cone is to reduce the aerodynamic drag, because if the rocket was just flat on the top, the drag would just slow it down. So that's why the rocket nose cone is always sharp, that it can go with less drag. This one is plastic, but we also use like metal and fiberglass nose cones. This transition piece is attached to our top tube, and it's this red piece here. This makes it so that the diameters of the two tubes can connect to each other. And this angled piece is also for less drag. The bulkhead is this wooden piece right here, and it has a eye bolt attached to it, which is attached to a shock cord. And then this shock cord is not attached to anything right now, but it would be attached to the bottom tube and a parachute. And this is used to secure the two tubes together so that they don't split apart during launch. Fins. We have the fins right here. These ones are tubular, but like the bottom picture, but we also have triangle fins like the top picture. We use the triangle fins for our NASA student launch rocket, and this is for our TARC rocket. And the motor retainer, the motor holder, it's on the bottom tube right here. And it's used to hold the rocket motor in place. And if you unscrew this piece, you can put in a motor and then re-screw it on to hold it down so it doesn't fall out. Our recovery system is a parachute. The parachutes create a lot of drag, so the rocket can come down pretty slowly and safely, and we can reuse the rockets for multiple launches. The altimeter is this little circuit board with things attached to it right here, and this tracks flight data, altitude and speed, and how long the flight took. So we use these in all of our rockets, and it's usually required for the TARC competition and NASA student launch competition. So this is our rockets theme for our NASA student launch competition, When Rocketry Meets Biology. And our rocketry rocket is overviewed here. It's 183 centimeters long, weighs approximately 16 pounds, and its expected apogee, where it goes the highest, it's going to be 4,500 feet. Maximum velocity and other information is also listed here. Now, the main materials we use are fiberglass because it's strong and doesn't weigh too much. The main body is made of fiberglass, the nose cone is made of fiberglass, the fins are made of fiberglass, and the streamer and parachute are made of ripstop nylon. These are also very durable materials. The streamer is basically a substitute to the parachute. It's just like a ribbon kind of, and it also slows down. And the glue we're going to be using is epoxy because it secures it very well. All the different parts need to be very secure so it doesn't blow up during launch. Now, a recovery system has the streamer, and at apogee it will deploy, and at 600 feet another parachute will deploy, and both recovery systems use black powder charges so they can eject. And for our truck rocket, it will naturally eject by itself because it's just cardboard. It's not really too much holding together. But for the NASA student launch rocket, it's fiberglass, and it's screwed together with shear pins, which are nylon screws, so they will shear off after, like the black powder charges set off, which makes sure the ejection does occur properly, and so the rocket doesn't come apart too early. Now, our subscale flight was successful. We have data over here from the altimeter. We have a picture of a rocket going up, and we have our ground test, which is a test on the ground that we checked if the ejection charges work properly, and they're charged and controlled by the altimeter, which we said earlier. These tests make sure that we can launch knowing that our ejection will work properly and our rocket can deploy its parachutes. Our payload design was to solve like a science experiment, and it's made of 3D printed plastic. It's going to be mimosa critical plant experiment where we see if plants are affected by rocket forces. The mimosa pudica plants, they are touch sensitive, so if you touch them, they will react to it. We're going to see if that affects anything in rockets. This is a drawing of our design. We have some cameras on the top, some plants in the middle, and a weight, so it keeps it balanced on the ground or level with the ground. There's also a light on top, so the plants will get equal light during flight. And this tumbler design makes sure the payload stays level during flight and it doesn't tip over and dump the plants out in the payload somewhere. So mimosa pudica plants, they're pretty small right here. They're touch sensitive, and we have to grow them so they can be controlled and all grow at the same time. We're gonna have 3 inside the rocket and 3 on the ground as a control group. For our cameras and light, we're going to be using these keychain cameras because they're small and they will fit in the payload very well. And we'll use LED lights so the payload plants can get equal light. These cameras are motion sensitive, so they will start recording when the rocket starts going in motion. Everything with the payload is 3D printed because it is replicable and we can make new designs very easily and create them in hours. After the launch, we have to see data analysis to see if there's correlation between the rocket forces and altitude. And we also see if habituation, which is when repeated exposure to a certain thing makes the plant less responsive to it. And we're going to see if the mimosa plants can be habituated in the rocket forces / altitude experiment. And thank you for listening to our presentation. If you have any questions, you can do a Q&A right now. We will also put like a video right now of our rocket. Sorry, I forgot to share something.
We're going to launch this in 5, 4, 3, 2, 1. Waiting for
You're trying to launch? What? Get Mark's text?
Rocket launch. The song again. Oh, that's nice.
No. Okay. Do my phone.
Range is clear. Sky is clear. 5, 4, 3, 2, 1.
This is one of our ground tests, and as you can see, it didn't work. If it works, it's supposed to eject like completely off. And this is what the first one, and we did another one, and it worked.
Clear. Sky is clear. 5, 4, 3, 2, 1.
Okay, we're NASA student launch. We're gonna launch this in 5, 4, 3, 2, 1. Okay, nice launch up. Waiting for 5 minutes.
Thank you for listening to our presentation. We'll be here for another 5 minutes if you want to have any more questions in the chat or if you want to unmute. And thank you for listening.
Good job.
Thank you. Thank you.
Good job. Good job.
Thank you. I put my email in the chat, so if anybody has later questions, they can just email. You can email me directly. We hope this presentation introduced you to rockets and makes you interested in learning about more of rocketry.